Hello everybody and welcome to today's video, which is going to be an introduction to Extrema. So here we go, intro to Extrema. And at this point, talking about Extrema, we know what a derivative is. Um, so, we're going to use that. And let's just jump right in here. Um, so let me make a little XY grid here. And, the Extrema thing isn't so crazy. We're talking about max and mins. That's what we're talking about. So, to keep it as straightforward as possible, if I can make a curve here. So I'm going to start a curve off here. And let's look at a couple things, all right? So for the most part, it's just as straightforward as it looks. So, for example, here, this point here, this point is lower than all the other points in its little neighborhood. Okay, so here's its little neighborhood. This point is lower than all of the other ones, so this one is going to be a minimum. Okay, now let's look here. Okay, let's take note of a couple things. First of all, notice that this is the highest point in its little neighborhood, but it is not the highest point everywhere. Like, here, this point is higher. So this will be what we call a local max. Okay, so a local max or a local min is a max or a min that is higher or lower, depending on if you're talking about a max or a min, than anything in its little neighborhood, but it's not necessarily the highest point on the whole thing. Okay? Now, in this particular little example here, I want to emphasize that we have these little points here. Okay? So these are end points. Okay? So let's say, for example, I'm just going to pick some numbers here. Let's say that this is x equals, I don't know, let's say -5. And let's say that over here is x equal +6. Okay, so therefore what we have is we have a continuous curve, meaning that we don't have to lift our pencil, right? A little review there. We don't have to lift our pencil when we sketch from -5 to 6. So we have a continuous curve on this interval, -5 to 6, with the brackets. And so what this means, if your curve is continuous on an interval, then Extrema is guaranteed. Okay. Extrema is guaranteed. Okay. Now we've spent some time already talking about the maxes and mins on this thing. We haven't talked about everything. Let's go through these other ones here. Here is going to be a local minimum. And let's look at this guy. This guy right here. First of all, notice it's an end point. Okay? So the point here is that endpoints are important and endpoints must be tested. Okay? As we can see here, this is the highest point on this entire curve from -5 to 6. So this is going to be what we call an absolute max. We also call it a global max, or absolute or a global max. I'm just going to write absolute max here. Okay. And the reason it's an absolute max is because it is the highest y value that is attained on this interval. Okay. In other words, whatever this y value is, let's just say, let's keep it simple. Let's say this is y equals 10. Okay. So the absolute max is y equals 10. All right. And the reason for that is because y equals 10 is never exceeded. Is there any point on this function where y is above 10? No. No. Okay, so it is the absolute max. Okay. Very, very nice. Okay, now let's get a little bit more sort of into the details here. Let's look at derivatives now. Okay, so let's look at this minimum for an example. If we look to the left of the minimum, notice a few things. Notice that f is decreasing to the left of the minimum. Okay. Once again, f is decreasing. This means that the slope of f to the left of the minimum is negative. Okay? And on the other hand, to the right of the minimum, notice to the right of the minimum, the function is increasing. Okay? And a way that we can say that with derivatives is if our function is increasing, our derivative is going to be positive. Okay? So in other words, at the min, the derivative dy dx changes from negative to positive. Okay? And this is how we define a minimum. Okay? So if you were ever tasked, and you will be tasked with this, if you were ever tasked with showing that something is a minimum, if you have to justify your answer, and you always have to justify your answer, is you're going to show that to the left of the minimum, the derivative is negative, and to the right of the minimum, the derivative is positive. But that is not enough. Okay? There's one more thing that we have to keep in mind. Okay, and that is what happens at the minimum itself. And there's two possibilities. Here is the first possibility that we can see right here. What is the slope at the minimum here? What is the slope of this purple line? The slope of this purple line, you guessed it, is exactly 0. Okay? And I know I'm just kind of adding stuff as I go. Let's say this is x equal negative 3. Okay? So here's the point. Here's the point. For this minimum, the derivative at negative 3 is exactly 0. The slope at negative 3 is exactly 0. So this is the first thing that we have to show. All right? And by the way, a little more vocabulary here. Whatever the x value is, where the derivative is 0, this is called a critical number. Okay? Critical number. And I am not spelling things right. Critical number. Again, critical numbers are found when you set the derivative equal to 0, and whatever that x value is, that is your critical number. You can also find critical numbers by taking your first derivative and setting it equal to undefined. And we're going to talk about the undefined thing in a separate video, because I want to make sure that we understand that. But anyway, this is how we find the critical numbers. The critical numbers are... why are they critical numbers? They're critical numbers because they are candidates. They are possible locations where a max or a min could occur. So they are candidates for Extrema. So not every critical number is going to result in a max or a min. But one thing that we can say for sure is every max or a min will have a critical number associated with it. Okay? So good. So now let's look at the maximum here, and we can go through this a little faster because it's the same type of reasoning that's just in reverse. Okay, so if I look at the derivative, let's do yellow for derivative here. If I look at, here's the max. If I go to the left of the max, notice the function is increasing. And just like we said a little bit ago, an increasing function is going to have a positive slope. And look to the right of the maximum. To the right of the maximum, the slope is negative. It's the reverse of this situation here. Here we go from negative to positive. Here we go from positive to negative. Okay? And also, like we said, at the max, at the max, we are exactly zero slope. Okay? So, if you're at a max, if you're at a maximum, what's going to happen? Well, one, the derivative changes from positive to negative, okay? And we also have the derivative at the location, at the x value, has to be either 0 or undefined. And once again, we're going to cover the undefined case in a separate video. But there we go. This is it, really, for the most part, aside from the undefined thing, okay? Any continuous closed curve, you're guaranteed to find extrema. A max and a min. Okay? So all you need is continuity to guarantee extrema. If you have continuity, you're going to have extrema, 100% guaranteed. Okay? So then, how do we find them? Well, the maxes and mins are going to happen when the derivative is 0, when the slope is 0. Or undefined. And again, that's going to be a different video. But here we are, right? Oops, that doesn't look very good. Let me try that one more time. There we go, right? Slope here, also 0. Okay? It's a minimum, so to the left, our slope is negative. To the right, our slope is positive. Slope went from negative to positive, therefore, we have a minimum. Okay? Very, very cool. Let us see how much time has passed. 13 minutes. Let's go through an example. Okay. Let me do one that's not so crazy. Let's do a good old polynomial example. Okay. So here we go. Example 1. Our function is going to be this bad boy right here. X to the 3 plus x to the 2 minus x. Okay? And I'm not going to plot this thing in advance. I'm not going to do that. We're going to go through the process that we just talked about, which is this whole thing. Okay? We're going to find our critical numbers. All right? So, trying to find maxes or mins, we know that the slope at a max or a min has to be, again, either 0 or undefined. Now, this is a polynomial, so there's no possible way it can be undefined at all. It's defined everywhere. Its domain is negative infinity to infinity. So we don't even have to worry about setting every function equal to undefined, because not every function is going to have an undefined solution. Anyway, here's the derivative of the top function here. If I set this equal to 0, I now have to solve the quadratic equation. And, you know, good thing we learned how to do this in pre-cal, right? 3 times negative 1, negative 3. Now I need two numbers that multiply to negative 3 but add to positive 2. That's going to be plus 3 and minus 1. Okay, now we multiplied by the 3 in the beginning. We're going to divide by that bad boy, and we're going to reduce wherever we can. This reduces to 1 over 1. This reduces to negative 1/3. What are we left with? We're left with x plus 1 and then 3x minus 1 equals 0. This gives us two solutions. One solution, x equal negative 1, or add 1 divided by 3, x equals 1/3. So these are our two critical numbers, all right? And now, you know, again, we're trying to find maxes and mins, okay? Maybe I should write that. We're trying to find maxes and mins, people. Okay? So what we're going to do is we are going to split the domain according to our solutions. And, you know, if you had me in pre-cal, we did this all the time. And we did it, you know, for this kind of reason, because you have to do it in calculus. Here we are. All right. From, you know, the domain and negative infinity to infinity, the first solution we encounter is going to be negative 1. Okay. And then negative 1 to 1/3. And then after 1/3, we have nothing left, so we're going to infinity. So we've split the entire domain, negative infinity to infinity. We've split the entire thing according to the critical numbers. That's what these are, critical numbers. We've split the entire thing according to their critical numbers. And now we're going to test and see what the slope is, right? So here I'm going to test with negative 2. Here I'm going to test with 0. And here I'm going to test with 1, right? We got to pick numbers that are inside the intervals. Don't pick the endpoints themselves. It's not going to work out for you. Now, here's the factored form. This is the easiest place, in my opinion, to test these guys out. Negative 2 plus 1, that's a negative. 3 times negative 2 minus 1, that's another negative. Notice I don't care what the number is, right? I just care about the SIGN, the sign. So this is positive. Okay, so our function's increasing. Our function's increasing from negative infinity to negative 1. All right. So here we have first derivative is positive. All right, now, if I plug 0 in, 0 plus 1, yeah, that's going to be a positive. And then 3 times 0 minus 1, that's going to be a negative. Positive times a negative, well, that's going to be a negative. And a negative is definitely less than 0. Okay, so, you know, our function goes from increasing to decreasing. Okay, and now let's throw 1 in here. All right, so 1 plus 1, we know what that is. Positive. 3 times 1 minus 1, that's another positive. So 2 positives, that's a positive. Positive bigger than 0. We're increasing. Woo! Very, very cool. Okay, so now let's think about what's going on. Okay? So we have already shown that at negative 1 and 1/3, at the critical numbers, we've already shown that the derivative is 0. Here's a derivative. Set equal to 0. Here's our solutions. Critical numbers done. Now, after that, we showed, using our critical numbers, we showed that our function went from increasing to decreasing. Well, let's think about what that means, right? What does that look like? It's a very simple image, right? And simple images is what guides us in this class. Okay, if we go from increasing to decreasing, it means we have a maximum. Okay, so this was the location that we were looking at, the -1. Okay, so therefore, but because of this, because of these two pieces of information, therefore we have a max, a local max, at x equal -1. Okay, we've justified it. Derivative went from positive to negative, so there we go. Okay, now decreasing to increasing. Once again, what does that look like, right? Decreasing to increasing looks like this, and that means we have a minimum, and the location of that minimum is going to be here at 1/3. Okay, so therefore we are going to have a local minimum at x equal 1/3. All right. Okay, very, very nice. Okay, so now, just by using this information, we can get a really fairly accurate graph of this function. Okay, so I guess the only thing that we don't know is the y values of the extrema. So let's calculate that, and then we'll make a quick little graph here. Okay, so we need -1 and we need 1/3. Okay, so I'm trying to find the y value of extrema now. -1, f and -1. Well, I'm plugging it in here. All right, -1 cubed is -1. -1 squared is 1. And then minus -1 is +1. And that's just going to be 1. All right, so in other words, -1, comma 1. That's the first point of extrema there. That's going to be our maximum, actually. And now for the minimum, okay? Minimum, f at 1/3. Well, 1/3 cubed. That's going to be 1/27 plus 1/9 minus 1/3. So, common denominator business, 27. So 27 plus 3 minus 9 over 27. 30 minus 9, 21 over 27. That's weird. That's weird. Holy crap. Okay, fair enough. All right. So we wind up with 1/3, comma 21 over 27, and that's actually going to be our minimum. So not a lot of variation here. 21 over 27 is pretty close to 1. So now can we make a little graph? Well, yes, we can. -1, comma 1. So -1, 1. This is going to be the maximum. And 1/3, well, okay. If this is 1, then this is 1. Well, sort of. It's probably a little less than 1. Let me try again. Okay, that's a little too far to the right. Whatever. You get the idea. 1/3 is roughly here. Okay. And 21 over 27 is going to be a little bit less than 1. Kind of like that. All right. And so, yeah, let's remember. We have a maximum here. So the function has to do something like this. Doesn't look very good. Hold on. Try that again. Yeah. We have a maximum here. And a minimum here. Maximum here. Minimum here. Just like that. All right. Very cool. Yeah. So that function is going to look roughly pretty close to that. Okay. Whew. Okay, I think I'm going to call it for this video. We have an introduction to Extrema, maxes, mins, and a full example. We'll call it.